How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at the change of concentration with time. So our objectives will be to determine how much reactant or product remains or was produced for first and second order reactions over time, and to use the rate laws to determine the half-life of first and second order reactions. So let's talk about concentration over time. So as a reaction proceeds, the concentration of reactants decrease and the concentration of products increase. That should hopefully make a lot of sense to you. You're using up the reactants and you're making some products. So reaction rates decrease as time goes on because we're using up those reactants. Things are going to go slower as time proceeds. So how can we calculate the amounts of the reactants at any given time? You know, if the reaction rates are constantly changing, we can't just use the average rate because it's changing over time. How are we going to know how much stuff we have at any given time? So you're going to have to start with the rate law expression, or the equation, and then some calculus magic is going to happen, and then you're going to get a new equation, and then that's, how are you going to do it? You're going to use this new equation. So for first order reactions, you can see we have the rate law on the left, where the rate equals K times A. It's the first order, right? So only first order. Some calculus magic, and we get this handy-dandy equation that you can memorize, you can write it down, but it's going to be one we refer to a lot. So it's the natural log of the amount at a given time equals the negative K, which is the rate law constant, times time, plus the natural log of the starting amount. Right, so AT is the amount at a given time, K is the rate law constant, and A0 is the starting amount. So for second order reactions, we start with rate equals K times A to the second power because it's second order. And we get some calculus magic going on, and we get a new equation that looks like this. 1 over AT, which is the amount at a given time, equals KT, K being the rate law constant, T being time, plus 1 over the starting concentrations. So a little note. The calculus magic. I'm sure you're all wondering what that's all about. We're not going to cover the calculus in this video because we don't need to, right? We just need to know and be able to use the resulting equations. If you're curious, I'm sure you can find stuff out there that will show how you get from A to B. First order reactions, this is the equation you need to know. Natural log of the amount at a given time equals negative KT plus the natural log of the amount you started with. Second order looks a little different. It's 1 over the amount of time. 1 over the amount at a given time equal KT plus 1 over the starting amount. So concentration over time in graphs. How can you know if you got first order or second order? Well, one way is to graph all your data and to change your axes for what you're graphing with. So we know first order reactions follow this equation. And the reason why we set it up like this instead of solving for the amount at a given time, why we kept it in terms of natural log, it's because it follows a real nice y equals mx plus b formula. So we can plot a straight line when we plot these values. ln of AT is our y, our slope is going to be negative k, x is going to be our time, and our y-intercept is going to be the natural log of the amount we started with. So if that gives you a straight line, then you know you got a first order reaction there. Second order reactions, again, why do we have 1 over the amount at a given time? Why do we write it that way? Same reason we get a nice y equals mx plus b format. So we can graph that, where y is our 1 over the amount at a given time. Our slope is going to be our k. Our x is going to be our time. And our y-intercept is going to be 1 over the starting amount. So if that gives you a straight line, then you know you have a second order. So look at the axes for your graphs, and that'll help you figure out which one it is, first or second order. Example problem. It has been determined that the first order reaction, x plus y makes z, has a rate law constant of 5.91 times 10 to the negative 4 per second. If the initial concentration of x was 0.0100 molar, what would its concentration be after 100 seconds? So again, we want to know how much we have at a given time, so we're going to have to use that first order equation. So natural log of the amount at a time equals negative KT plus the natural log of the starting amount. So to get rid of this natural log thing, you got to put both sides to the power, or e to the power of that side. So basically, it's e to this whole thing, and that gets rid of the natural log on the left side. So now we have the amount at a given time equals e to the negative KT plus ln of A0. So then you just plug and chug. Now we've done the rearranging. We haven't messed with any numbers yet. Now we can plug in some numbers. So it's going to be e to the negative k. So we have 5.91 times 10 to the minus 4 as my k. My t is the 100 seconds, and this is my ln of a0. So just kind of plug that into a calculator, and you get the answer, and there you go. That's how much you would have. That's the concentration at that given time, just by doing that math. So let's try a second order equation. It says the second order reaction 2x makes z has been determined to have a great law constant of that number, 9.63 times 10 to the minus 3 per molar second. How much x would remain after 150 seconds if its initial concentration was 0.1 molar? So again, start with the second order equation. 1 over the amount at a given time equals kt plus the 1 over the starting amount. So again, how do we get at to become the only thing on that side, and preferably on top? Right now it's in the denominator, so we want to get rid of that. So the way you do that is you take the reciprocal of both sides. You divide 1 by that side to both sides. Keep change flip, you get the amount at a given time equals 1 divided by this whole side. So now you just plug and chug. So 1 divided by k, 9.63 times 10 to the minus 3 per molar second, times the time, plus 1 over the starting amount, and then you got the answer. And that's all there is to it, really. You know, you might have to rearrange it and do some algebra to solve for a different value. Maybe you need to know the time instead, but that's just algebra. Half-life. Maybe you've seen Half-Life before when you're talking about radioactive decay, but you know, Half-Life doesn't have to be just for radioactive decay. Half-life is the time it takes for the concentration of a reactant to drop to half of its original value. So we're going from 100 to 50. Right, that's one half-life. We're going from 50 to 25. That's another half-life. It's just how much time does it take for it to drop in by 50%. And it's a nice way to describe how quick a reaction is. If you say, like, hey, a half-life is 100 seconds versus 100 years, you get an idea for how quickly or slowly that reaction actually is. So a shorter half-life equals a quicker reaction. So to solve for half-life, which is a time, so you need to know how long a half-life is, you simply use those kinetic equations and plug everything in and solve for t. So let's take a look. First order reactions. All right, if it's at 1 half-life, we know the amount at that time is going to be 1/2 the original amount. Right, so we know that at equals 1/2 the starting amount. So we can just plug that into the equation. Substitute 1/2 a0 in for at, and now you have an equation where, you know, t 1/2, you're trying to solve for that. There you go. And then you just do a little rearranging. So let me get, you know, t on one side by itself, kind of. So I got to subtract ln of a0 on both sides and do a little, you know, log rule stuff. 0.5 a0 minus a0 equals, you know, 0.5 equals negative k. You know, you do the algebra. And you end up with this equation. The t 1/2, or the half-life, is equal to negative natural log of 0.5 divided by k. And that's true for all first order. So this is for first order reactions. So you can tell by the equation the half-life for first order reactions only depends on K, and it's unaffected by the initial concentrations. And this is a lot like what you may already know about radioactive decay. It doesn't matter how much you start with, the half-life is the same regardless. You start with 100 grams of carbon-14, the half-life is always going to be the same. Doesn't matter, you could have 1,000 grams of carbon-14. The amount of time it takes for half of it to decay will always be the same for first-order reactions. It only depends on K. So if we take a look at second-order reactions, it's going to be a little different, but we do the same process. So at one half-life, I know the amount at that time is going to be equal to half of the starting amount. So I can plug that in to that equation and then do the same process, rearrange and solve for T1/2. Right, so there we go. So between here and there, I had to address the fact that I had 0.5 in the bottom. So I just, distributed that. I get 2 over the starting amount minus 1 over the starting amount, which means I'm going to end up with 1 over the starting amount equals K T1/2, and then rearrange. I don't know why I put this. Oh, all right, yeah. So there you go. So this is what you get for second order equations. And you can see that the half-life depends on K and the initial amount. So it depends on how much you start with. The half-life will depend on the starting amounts. So the half-life is also going to change as the reaction proceeds. So, the half-life to start with isn't going to be the same thing as if you go, all right, hey, it's been 100 seconds. What's the half-life at this point? Because you have a different new starting amount, it's going to be different. So you don't need to memorize these equations in addition to the other equations if you can solve for them. So if you can remember those processes, you go, all right, let me substitute in the values at 1 half-life and solve for T1/2. You don't have to memorize these. Otherwise, maybe you would feel better just memorizing. But this is what they are. First order, this is the equation. Second order, that is the equation for the half-life. All right, summarize. Can you determine how much reactant or product remains or was produced for first and second order reactions over time? That's the big one, right? Can you use the rate laws to determine the half-life of first and second order reactions? That's the second important objective. And that's pretty much it, right? So, yeah, that's it. Hope you found that helpful. If not, I failed you. I'm sorry. Okay, bye.